In this project and presentation, I will report out the recent progress of printed non-fullerene organic solar cells to achieve higher performance. Over here, three journals are selected. So the first journal was printed non-fullerene organic solar cell with the highest efficiency of 9.5%. Second one would be the effect of solvent additives on the morphology and device performance of printed non-fullerene acceptor-based organic solar cells. And then the third one would be the digital inkjet printing of high efficiency large area non-fullerene organic solar cells. So these journals were taken from 2018 to 2019. So let's go on the first journal over here, which is the printed non-fullerene organic solar cells with the highest efficiency of 9.5%. In this first journal, uh, it is actually reporting on the highest power conversion efficiency, which is PCE, of 9.5% ever reported using Dr. Blade printing techniques for non-fullerene organic solar cells, or SC in short, in a flexible large area, which is 2.03 centimeters squared on ITO free with the base of PTB7, TH donor, and ITIC acceptor. So the process was aided with a 0.6% volume percentage of 18-DO, and this is a solvent additives, which is contributing in nanoscale phase separation, prolonged dynamic drying of Dr. Blade printing, and helping in migration of ITIC molecules in the drying process. This work has reported that it can achieve higher PCE than that of currently spin-coated counterpart or the current technology of 5.86%, and the results were taken from morphology analysis, crystallinity, charge recombination, and transport of the active layers. So we're moving on the research methodology of this journal. So note that the methodology details were not reported out in details. However, what was managed is the step-by-step from the reading across the journal. So first of all, the acceptor and donor were dissolved in chlorobenzene with 1 to 1.3 weight ratio. So the first one over here, PTBZ TH is the donor and ITIC is the acceptor. And then after that, 1,8-dilodoctane, which is DO. This is the solvent additive. It is added into the solution over here. And then these were sent into the spin coating techniques to produce the active layers. Okay, in parallel, the same method or the same step was produced also. However, it was produced in Dr. Blading techniques. So you can see here, this is actually a comparison that will be reported out later on. So the spin coating techniques, it serve as a reference, and then what the journal is trying to find out is the Dr. Blading techniques. Okay. So the active layers are already produced over here. And then now we need a substrate. So over here, the glass or ITO substrate were selected. So this is the first substrate. And then another one, we would have the PEG, AG or silver, and TIO substrate. So these two substrate will go, each of the active layers will be printed on top of each of the substrates. So you can imagine that there's like 4 matrix over here. And then all this will go into the deposition of the consequently layer, which is the deposition of MO oxide, and then followed by silver on top of this substrate, okay, respectively. And then in the end, some analysis were done onto this finished OSC, and then which are the photoluminescent and electroluminescent measurement, EKE measurement, and then it also analyzed the inner structure of the, I would say, the active layers, then analyzing the morphology of the printed thin film using SEM and TEM, and the JV measurement. So going into the results and discussion of this journal. So over here, I have a summary from the journal itself, in which it talks about the two active layers just now, which is ITO base class and also ITO free pad, with two different fabrication method, which is total blading, which this journal has interest with, and spin coating as reference, and then with various ratio of DO concentration. So basically, this table summarizes with three different variables over here. What would be the results out of it? So the JV measurement was reported out, the field factor as well as the PCE, the maximum PCE achievable. So when we're just taking a first glance over here, you can see that there's 9.4% of maximum PCE reported out, and this is using ITO base class, Dr. Bleeding fabrication method, and 0.6% of DO. And in regards to that, we also have a very high field factor, which is around 71%. Next, we'll go to the photoluminescent and electroluminescent analysis. So over here, we have a spectrum. And then at the top here is the normalized photoluminescent intensity, and the bottom one is normalized electroluminescent intensity. And over here, what was reported out was the individual, or the acceptor and the donor itself purely, as well as the blend. So the blend means like the blend in between of these two the donors and the acceptor, with the addition of different concentration of DO. So in short, what we are seeing over here is the individual, or the pure ITIC, which is the acceptor, has the highest photoluminescent intensity, and then followed by the donor. However, with the blend itself, we can see like there's a flat graph, especially on the reported 0.6%, which maximum PCE, and this actually indicates that the blend heterojunction is well mixed. Then following the chart at the bottom here, 0.6% of the DO volume showed better and higher electroluminescent intensity curve, especially when we're talking on 900 nanometer going towards the 1000 or 1100 nanometers. Then next, relative intensity measurement, ITIC distribution in BHJ also was measured and reported out. So on the top here is the graph of the intensity of ITIC, and then the binding energy. So we have like this peak is the binding energy, and pure ITIC, of course, will have the highest relative intensity. However, following the concentration, so with 0% DO, it has lower ITIC concentration, followed by 0.6% and 1%. Okay. And then interestingly enough, at the bottom here, so this is the illustration that shows the PTB7TH, which is the donor, and then ITIC, which is the acceptor, with a combination of different concentration of DO. Okay, So what you can see here, for 0% volume, both the acceptor and donor is like concentrated at one side. And then the same thing happened at 1%, 1 volume% of DO. It is concentrated on one side. However, when we're talking about 0.6 volume percentage of DO, it is well mixed. And this is actually more favorable because it is a homogeneous mixture. And this it will contribute to an increment of device current density as well as a fill factor. Next, we'll go to the second journal, which is the effect of solvent additives on the morphology and device performance of printed non-fullerene acceptor-based organic solar cells. So in summary, this journal is reporting an increase of average power conversion efficiency, PCE, from 3.5% to 7.9% with addition of solvent additive, which is 0.25 volume percentage concentration of 1,8 DU into the active areas of conjugated polymer with benzodiethiophene units. So PBDBTSF, which is the donor, and nonfullerene small molecule acceptor, which is IT4F. And these are printed using meniscus guided slot die coating. So the effect of different solvent additive on material surface morphology and inner nanostructure were studied with regards of different solvent additive concentration using GSEX, GWAX, SAM, and FM. Moving into the research methodology of this journal. So first of all, photoluminescence measurement was done on the pure acceptor and pure donor respectively using this machine. And then it is dissolved in the chlorobenzene to obtain 7 milligram per milliliter solution, which is stirred at 48 hours at 100 degrees Celsius. And then there's an addition of 1,8 DO. So this is with different concentration as the study suggests. And then in parallel, microscope glass substrate were cleaned in mixture of 50 milliliter deionized water, 80 milliliter of hydrogen peroxide, H2O2, and 180 milliliter of H2SO4 for 15 minutes at 80 degrees Celsius. And this microscope glass later on will be dried with nitrogen gas and then plasma for 10 minutes using oxygen plasma. This is to further clean up the surface and enhance the wettability. And then once this substrate is clean, it is ready to conduct the slot die coating at room temperature, and film thickness of 100 nanometer is achieved. Okay, so before going further into the other processes, some measurements were taken at this stage, which is the active layer stage. So over here, some analysis were done on the inner structure of the heterojunction or the planned heterojunction OSC using GSEX and GWAX. And then same thing, some morphological analysis were done on the printed thin film using SAM and AFM. And then subsequently, photoluminescent and UV VS absorbent measurement were also done, as well as the EQE measurement. So after that, before proceeding to the printing of this active layer onto the substrate, room temperature. The substrate were first purchased and also prepared beforehand. So over here, indium tin oxide ITO coated glass substrate were purchased, and then it was cleaned with Alconox deionized water acetone isopropanol, and then going for O2 plasma, then going for the precursor solution, which has been coated on this substrate and annealed at 200 degrees Celsius. So then it is ready for the active layer printing on the substrate itself. After this was done, the final steps to complete the device itself is printing out or thermally evaporate the MOO3 layers and aluminum under vacuum condition. And then finally, the IV characteristics were obtained from this device. So under results and discussion at the active layer level, so the surface morphological analysis from SEM and TEM images. Over here, the gray photo shows the SEM images, and then the orange or gold photo here, it comes from TEM. Sorry, AFM. And then different concentration of DO was tested, which is 0%, 0.25%, 0.5%, as well as 1%. So over here, this two photo is with the 0% DO concentration, and then 0.25%, 0.5%, and 1%. So at 0% concentration, you can see that it's more closely packed. The structure is more closely packed and overlapping. So this actually creates unfavorable condition for OCS due to the reduction of interface area. And then increasing the concentration of DO itself. So you can see that the surface is slightly roughened, and actually this indicates that there were interpenetrated network formed and actually helping in aiding the charge transfer in the active area. So this is favorable. But then when we increase the amount of DO concentration, you can see that the structure is creating more and more gap. You can see. And then these figures actually suggested that the small structure form actually creating bigger distances, so bigger gap, and this could increase the risk of charge trapping and hindering transportation of charges to electrodes. So this is basically unfavorable. Next, let's take a look at the photoluminescent results that was measured. So over here, we have the pure donor and the pure acceptor, as well as the blend acceptor donor solution. And we have it is reported using wavelength as well as luminescent. And over at the right hand side, it shows how different volume is affecting on the luminescent as well. So measurement was taken. Okay. And then pure materials actually show higher luminescent intensity, while if it's blend, it shows lower luminescence. So another item to note is this donor has a wide range, like it can cover like wider range of wavelength, which actually suggests that it can accept multiple wavelength to interact. And then another graph is actually showing how this combination affected with a different concentration as mentioned earlier. So over here we can see that with zero, if we're not adding the DO concentration at all, it has like very high luminescence as opposed to adding some of it, which is almost comparable. And then following up on the UV vis absorbance spectra. So over here, it is reported out with different concentration of the plants, different concentration of DO into the plant. So in short, let's talk about the dark blue line over here, which is 0.25% volume percentage. And it gives like the highest performance if we're looking across the 400 nanometer to 100 nanometer, as opposed to no concentration at all, meaning like not adding DO at all, as well as adding more DO concentration into the accepted donor solution. Then let's take a look at EQE analysis. So over here, similarly, let's take a look at the 0.25% volume concentration, since we do know that this gives the highest efficiency reported in this journal. So you can see over here from 300 to around 520 nanometer wavelength, it has surprisingly low EQE. But when it goes beyond 520 nanometers to around 780, then I can see that there's a peak or very distinctive EQE as opposed to other concentration. So it means that the 0.25% DO is more favorable with this 520 to 780 wavelength. Okay, and then the graph over here is actually showing the, sorry, I cannot really see how the current density versus the wavelength. So similarly as shown over here, when it hits over here, it hits like around 600 something, it is it has less current density, but then when it goes beyond, it has like very distinctive curve or current density as opposed to other concentration. Next, we're going to take a look at the PCE versus DO concentration analysis. So this is the PCE versus DO concentration chart, and then this is basically a table summary of how much the DO concentration or the volume percentage, and then what was the best PCE achieved, the current density, open circuit voltage, fill factor, as well as average PCE. So from this summary table, we're able to see like a very distinctive best PCE over here is achievable with 0.25% of DO concentration. And then moving on to the IV characteristic, you can see that 0.25 volume percentage has very high current density as opposed to other volume or 0% even. So we can conclude that with this results that 0.25 volume percentage has the best performance across other different concentration of DO with the identified acceptor and donor. Next, we'll take a look at the third journal, which is talking about digital inkjet printing of high efficiency large area non-fullerene organic solar cells. So in this journal, it actually discussed on printing high efficiency large area non-fullerene organic solar cells using digital inkjet printing method. And this was reported for the first time during at 2019. So actually, as the demand of renewable energy increased significantly, the production of commercialized solar cells to meet the market demand needs to follow suit. So in this case, it is this journal is actually targeting OCS. So this journal, it will use P3HT and OIDTBR, so acceptor donor inks for this digital inkjet printing. And this journal reported out that it able to realize using this ink with digital ink printing to print on a larger surface area, which is 2 centimeter squared devices, and then subsequently achieving as high as 6% device efficiency. So for the purpose to demonstrate this technique in this work, large area devices are fabricated in the shape of marine turtle, and this was achieved with 4.76% efficiency. This also showcased that the potential of inkjet printing process for the future intake. So we'll see. Let's go to the research methodology that was done. So first of all, we'll go on preparing the substrate itself. So in this case, or in this journal, it is using the ITO covered glass substrate, in which it is cleaned through and then go through the O2 plasma for cleaning and wettability, and in parallel to create this substrate. So we have this zinc acetate dihydrate and 21 microliter ethanolamine with 1 milliliter of 2-methyl-methoxyethanol to create the sol gel solution. So this zinc oxide, so after the ITO is already done, right, then the zinc oxide deposition was done, and then this was done by spin coating the sol gel itself on top of the substrate. And then it was annealed at 200 degrees Celsius. And then before going to the digital inkjet printing, we have to prepare the ink first. So the ink is from the donor and acceptor of P3HT to OIDTBR. And this was made with the ratio of 1:1. So before this even go to the digital inkjet printing, it was measured on its viscosity as well as the surface tension. So this is to actually understand the requirement that to go for the digital inkjet printing. So before going to the final, which is the digital inkjet printing event, this ink mixture was first printed on silicon oxide substrate, and this was done because it was meant to find out the refractive index and the coefficient of P3H3 or the acceptor and the donor itself. And then only we go for the digital inkjet printing with a set of parameters. So after it is printed, this will be annealed at 140 degrees Celsius. So after it was annealed, so this is basically the active area. So the active area, there are some measurement was done or analysis even. So the first one would be the surface morphological analysis, and then the film thickness measurement itself, as well as the UV visual measurement. Then after this was done, this was taken forward to finish the final device of OCS, OSC, sorry. So over here we deposit the MOO3 and silver using thermal deposition, and then some pattern was actually so-called printed out or using a laser system to achieve the desired geometry on top of the device. So over here, there are several patterns that was done, and one of it would be the Marin turtle, and this is the solar cell. And then finally, electrical measurement was done and EQE measurement. Going to the result and discussion, I have a table of summary here. So in this journal, there's a variation of drop spacing and temperature influencing the current density, fill factor, as well as the PCE of OIC. So firstly, what was done was it was done with the same acceptor and donor that was mentioned before, but with ODCB or dichloropenzane base. This is actually to find out first of all on what's the drop spacing that can gives highest PCE. So first of all, what was done was it was done on constant bed temperature of 42 degrees Celsius. So this is the deposition temperature, and you can see that the highest PCE achieved was done with a 10 micron drop spacing. Then subsequently, this 10 micron drop spacing is turned into a constant while finding out what temperature is the best to conduct this digital inkjet printing. So over here, it varies from room temperature up to 60 degrees Celsius. So with 10 micron constant drop spacing, you can see that with the maximum PCE achieved here is 6.47%, which was done at 60 degrees Celsius. And also, it yields up to 67.2% of fill factor across all the temperatures. Okay. And then the graph on the right hand side, this is also a summary. So after this was trial out, the objective for this would actually to bring in the eco-friendly inks. So eco-friendly inks over here, what was introduced is two different hydrocarbon solvent integration. So versus the ODCB. So ODCB here is a reference that was already found out before. So these two solvent is the eco-friendly, the hydrocarbon that is eco-friendly. So in short, or in summary, the xylene tetraline actually provide the highest PCE in between these two, and higher, although it has a slightly lower fill factor. And then moving on the third graph, or like the two graphs over here. So this graph is the showing the different hydrocarbon ink just now, the eco-friendly ink, based in comparison with ODCB towards the JV curve, as well as EQE on different wavelengths. Over here is on different wavelengths. So you can see over here, ODCB, obviously it has like the highest efficiency and the highest current density, but then it follows by xylene tetraline in comparison of the pure tetraline. So you can see that between these two eco-friendly base ink, you can go for xylene tetraline since it gives like higher EQE and higher current density. And then lastly, from the results and discussion, so this figure it shows like the PCE chart across different areas. So multiple devices were printed with different area, and then the biggest area that was achieved during this inkjet printing was 2.0 centimeters squared. Yeah. So from this chart, you can see that with the smallest, which is 0.33 centimeters squared, we are achieving around 6% PCE. But then when we increase the area size itself, the PCE is actually comparable. So in short, that even with the increasing of area, the PCE still can be maintained, which is a good thing. So this actually indicates that in the future, that might be potential that with bigger area, we are able to achieve similar PCE or even better. And then the figure over here, or the chart. So this is with the current or JV curve. This is the JV curve of this marine turtle printed. So this is also a solar cell, which is very interesting. This shows that with this inkjet printing, it actually creates more door or open up more opportunities to create like beautiful so-called painting, but also it is usable for solar cells. So even with this was printed on 2.2 centimeters squared space area, and it's still able to achieve around 47% of fill factor and 4.76% PCE. So in short, this can create more potential in the future. As the overall comparisons, all the journals actually discuss on the innovation of new ways to increase efficiency of non-fullerene based OCS to tackle the issue of commercialization, enabling mass production, and also reducing the cost of non-fullerene OCS itself or the solar cell, as this has a huge market potential. So journal 2 actually discussed on the addition of 1,8-diol-solvent additives, which was proven to help on the PCE of the OCS. While journal 1 actually took another step forward by introducing Dr. Blade printing in addition to the solvent additives itself, and it shows that it can improve the overall performance of non-fullerene organic solar cells, as well as suggesting that it can be used in future mass production, while also giving the highest reported PCE among the 3 journals here. And then journal number 3, meanwhile, it took like a different approach to, I would say, a modern aesthetic point of view, and portrayed the potential of inkjet printing to be able to produce a desirable pattern while still serving its function and maintaining the PCE on larger area. As the overall conclusion for all 3 journals, so I have journal 1 over here, journal 2, and journal 3. So the first journal, it concludes of that the highest PCE of 9.5% were achieved by using blade printing non-fullerene organic solar cells, in addition of 0.6 volume percentage of DOS solvent additives, which help in creating favorable crystallinity, morphology, and internal donor acceptor structure in blend heterojunction. The second journal conclude that the improvement of average PCE was achieved from 3.5% to 7.9%, and maximum of 8.95% with the addition of optimized concentration, which is of 1/8 DO, which is 0.25 volume percentage, to the donor acceptor structure in blend heterojunction. However, higher 1/8 DO concentration, which will actually promote a declination of the device's PCE due to charge trapping provocation coming from the altered device structure. And then lastly, the third journal actually demonstrated the inkjet printing techniques use high efficiency large area, which is 2 centimeters squared, non-fluorine organic solar cells. So using commercially available donor acceptor inks, which is P3HT and OID-TBR, this technique able to produce up to 6.47% of efficiency with ODCP solvent additives, and actually offered eco-friendly choices or additives, which is 1,2-xylene that has the highest PCE of 4.43%. So this capability of inkjet printings, for example, the marine turtle just now, actually able to produce beautiful patterns, and it is something that should be taken note of in the future. So in summary, I prefer journal number 3 due to the reason that how the solution can provide not just the functionality, but it is interesting that it uh, can also provide the aesthetic value due to its ability to print any pattern, which can bring more potential in, let's say, architecture side as well as artist point of view, while also providing renewable energy to the community or city at that area. And then inkjet printing also suggests to unlock the potentials of mass production with cheaper and available materials, in which I would think that the current market would be very interested in it. However, more research need to be done in this case.